for different subgrade material on campus. And from this, we're going to provide alternative rehabilitation, alternative recommendations. The project need, we saw the need for the project. In the United States, 82% of all pavements consist of flexible pavements. Here on campus, 99% of our pavement is flexible. And what pavement is it's the largest asset for the majority of public agencies, which means that there's a lot to maintain, and there's a lot of money headed toward that because it requires, you want to protect these assets through maintenance. So we see this as very important. To start the project, it required a great deal of field work. We went out and collected traffic volumes and vehicle classifications, which would be used in our pavement design. The soil samples, also for pavement design, and our pavement survey, which consisted of windshield and walking surveys. The windshield survey being driving all the sections of road and assigning a PCI based on the ride quality, as well as a walking survey, which we looked at the sections more closely from the side of the road and actually made note of what type of distresses we're noticing and what type of distress caused to give us that certain ride quality. And from this, we use Micropaver, which is a database program with analysis tools to create a pavement management database. So now I'd like to hand it over to Nancy to discuss our traffic study.
We conducted traffic studies to determine the volume required for pavement design. We conducted an average daily traffic count at these 4 locations on campus for a 16-hour period from the hours of 6 a.m. to 10 p.m. All data collectors noted the number of buses and trucks that pass through each location. And also, we chose those locations because that's where we capture the heaviest traffic flow. For our ADTs, they range from 1,300 to 9,000, and the percentage of buses and trucks was about 3% for all 4 roadways. With our ADTs, we calculated our traffic index value, which is a measure of the cumulative number of easels expected during the design life of a pavement structure. Our TI formula came from the Caltrans Highway Design Manual, and our results for the TI were in accordance to the Highway Design Manual. And they range from 6.5 to 8. Now I'll hand it over to Chris to talk about geotechnical.
So I'm going to be talking about the sample locations that we had, where we sampled. I want to talk about the site conditions, and then I know we'll be talking a little bit about the soil classifications. So you can see from this picture here, from this photo here, that we can see 3 different sample locations. We chose these sample locations so that we would have the most diverse test results, which would best represent the underlying soils on the campus. This is about historical soils. We have unconsolidated sands and alluvial deposits. Also, with respect to faults and earthquakes, we have one major fault that goes to the campus, and that's the San Jose Fault. And this is a liquefaction map. And we can see here that our entire campus is within the liquefaction zone. We also know that our water table levels range from 2 feet to 20 feet. So this is our first site, MLOT. This is the highest elevation at 890 feet. This is our second site location. This is the middle elevation at 808 feet. And we can see that it's very green, and it's hard to see, but there's actually a hill slope right next to the site location. So our third site was actually at the Orange Grove, at the intersection of Citrus Lane and South Campus Drive. It was at an elevation of 731 feet, and we can see that this is actually the area right here. It's very dry, flat, and there's no construction, not well maintained. So next I'll hand it off to Aiden, who will speak about the soil classification summary.
Despite our broad range of locations, our soil classifications seem fairly consistent. As you can see, all 3 locations we have sandy silt, with the exception of 2 of them having gravel also. We've come to this conclusion by performing several geotechnical tests, such as We've also concluded that all of the 3 locations have excellent to good soil quality, which is perfect for pavement design. Next, I'll be talking about the R value. To get the R value, you have to perform what is known as the California Test 301, otherwise known as the state barometer test. What this test does is it measures the soil's resistance to an induced stress from a vertical load. This test is fairly popular in many industries in California, especially in Caltrans. The layer thickness is designed is based off the R value and the TI. So as you can see, the R value was incredibly crucial for us to have, and since our lab doesn't have the state barometer test, it's thanks to our sponsors that we were able to acquire it. When conducting this test, the soil needs to be in a state of saturation, and the sample is mostly normally prepared in 4 different moisture contents in order for us to have a better understanding of our R value. In the picture on your left, you can see the sample is being prepared, and on the picture on your right, you can see the state barometer pressing on the soil and measuring its resistance, as I mentioned earlier. Here we have a list of our R values. When you have an R value of 30 or greater, it becomes adequate for pavement design. And as you can see, all our locations are adequate, with our first location, parking lot M, having the lowest R value. That's the value we picked for our design basis, since that location is can take stress the least amount. Next, Nancy will be talking about pavement condition survey.
So we conducted pavement condition survey to analyze the distress and current road conditions for all of our campus roads. We had 3 teams perform visual and ride quality inspections. The distresses that we observed on campus were, some of them were longitudinal cracking, potholes, utility cuts, transverse cracking, and alligator cracking. Alligator cracking being the most common. Alligator cracking is due to an under-designed pavement structure, poor drainage, and heavy traffic loading. Our pavement condition allowed us to measure the condition of the pavement surface on a scale of 0 to 100. However, in order to simplify our analysis, we used a pavement condition index of 1 to 5, 1 being a failed road and 5 being a road in excellent condition. And here's how you would see a PCI of 5 would look like: a smooth ride, no cracks. The forms PCI of 4, PCI of 3, 2, and 1. 1 being a failed road, a road in very deteriorating condition, a very bumpy ride, and noise. In order to use the pavement condition index that we incorporated, we had to convert it back to a condition of 0 to a rating scale of 0 to 100, so that we can incorporate it into our micropaver software. For example, if we had a CPP PCI of 3, we used it would fall under the rating scale of 60 to 55 as a road in fair condition. Now I'll hand it over to Virginia and Sandra to talk about micropaver data.
Pavement sections analysis was done using micropaver software version 6.0. The software was originally developed by U.S. Army Corps of Engineers and distributed by American Public Works Association.
The first step in designing a pavement database is to identify the network, the branches, and the sections. The yellow line shown here represents the network, the red line, which is colored red, represents the branch, and the blue line represents the section. When inputting data into micropaver, it is important to input the right information. This information includes construction dates, PCI number, the section's length and width, and the inspection date. And I'll be talking about the pavement height model. On the y-axis, we have the pavement condition. On the x-axis, we have the time. This is our performance curve, which deteriorates as time goes by. You always want your pavement to be in the green section, since that's the acceptable condition. The when we were inputting data into micropaper, we realized many of our construction dates were missing, so we decided to use the payment life curve, which is this one right here. This is a best fit curve between 2 points. This point right here is the 2008 inspection date, and this point right here is the 2012 inspection date. When the curve hits the maximum PCI of 5, we move down to the x-axis to obtain the construction date that was missing.
PCI analysis was divided into 3 groups, Group A, Group B, and Group C. We also analyzed 3 types of roads: arterials type A, collectors type B, and residentials type C. The type of the road was based on the volume of traffic. So for arterials, we have 5,500 plus roads. For collectors, from 1,400 to 5,500 roads. And for residentials, under 1,400 roads. We also came up with this graph. It's a summary of condition for PCI. As you can see, all our arterials are in yellow, all our collectors in blue, and residentials in pink. And in the back, you can see all the parts which are in green, and this is a total of all the roads. On the vertical axis, you can see total area. On the horizontal axis, the condition of the roads. And all the conditions are ranging from excellent to failed. And as you can see from this graph, our roads are within, they're in the middle, and they're within a fair condition. So unfortunately, we don't have that many excellent roads, just a few. But it's a good thing that we don't have any failed roads. That's the most important thing that we want.
This graph right here summarizes the PCI for each group. Group A and B have an average PCI of 47. Group C has an average PCI of 33. Even though these numbers are below our red line, which represents the critical number 55, it doesn't mean that all the roads are in poor condition. Most of the roads actually have a PCI of 55 or above. It is only a few roads that have a really low PCI number, which bring down the average for the group's PCI number. This model curve illustrates the relationship between the PCI and the age of development. This curve right here should represent the arterial roads that we investigated. However, our results, we didn't get our expected results, so we just decided to use a generic curve that micropaper provides. Now this is an actual, the actual graph that we obtained with the collector roads that we investigated. As you can see, as the age of the payment increases, the PCI decreases. Most of our points fall above a PCI number of 55, which means most of the collector roads are in good condition. And this is our last model curve. This represents the residential roads we investigated. From looking at the graph, we can estimate that most of the roads need to be repaired between 25 and 30 years. We can also conclude that residential roads compared to arterials and collectors have the worst payment conditions, since our points right here are below the 55-34 number. And Eugenia will talk about the budget analysis.
We also ran budget analysis using micropaper, and we used 2 options. First one was for unlimited budget analysis, and it resulted in approximately $198,000 we need to spend. And another type of analysis was 50,000 per year restriction analysis. That was actually a requirement of the city. That's how much money they're giving us. It resulted in approximately $42,000 we need to spend annually, and a total of $211,000 for 5 years. And as you can see from this chart, if we have a lot of money, we have a limited budget, we eventually will spend less money. And now George will talk about structural pavement design.
For our structural pavement design, we elected to use the Caltrans method. Now, in order to use the Caltrans method, we need to know 2 pieces of information. We need to know the traffic index and the R value.